welcome to this course on FPGA based signal processing systems. We'll be doing sequential logic circuits. Sequential logic circuits, unlike combinational circuits, they have a memory element which is a part of the circuit. Here, of course, the combinational circuit which we had learnt in the previous lectures, that there is a combinational circuit which takes the input and the output of that would be depending on only the current input. It doesn't involve any past input or past output. So the past outputs of the combinational circuit are the states of the combinational circuit is fed back again as an input to the combinational circuit. So and the output depends on both the current input and the past values also. It can be a past input or it can be a past state or past output. So this is involving the memory element which stores the past values. So it can even store the past inputs or it can store the past outputs. Okay, so these memory elements are operated with the clock. So this can be enabled with a clock to retrieve this or to store the information or the bits or the data from here in the memory element. So with respect to the clock, every decision is taken in this memory element. So the sequential circuit, if we say it's a combinational circuit and the memory elements, whose output is depending on the current input and the past input or the past output values also. So the flip-flops and latches are considered to be this in the sequential circuits. So very simple flip-flop, if we take, that is D flip-flop, which can store the 1-bit information. So in that, if you consider this as a black box, and you might have seen the basic flip-flop structure, which contains the bistable elements, and then so and the feedback. So the D flip-flop, which is shown over here, it's a black box which takes the D input and the output is Q. There is a clock involved in it. So the clock, when we say, which is going to be ideally signal which is having this is two edges of the this is positive edge, and we can say this same clock, these are called the negative edge. So the flip-flop can be positive edge triggered or negative edge triggered. These are edge triggered flip-flops. So the time period is between the two clock edges. Similarly here also we can say between two clock edges. So at the active high and active low, the clocks also can be. So it's high and low, the clock will have. So the duty ratio of the clock can be adjusted and 50% on time and 50% off time, or it depends. I mean, so usually ideal clock has this racing edge which is very sharp, but practically if we see, there is a slope involved in the from 0 to 1 change the edge. So it's not a straight like what I had drawn here. It will have a slope like this. It will have a slope in the clock edge. So either it is a positive edge or negative edge. So there in the Verilog we use this pos edge and neg edge of the clock, where this pos edge and the neg edge are keywords. Okay, so the symbol, I think it is known to you that clock is now it is the positive edge triggered D flip-flop, this one. So if we have bubble in that in this place, then it is going, there would be a negative edge triggered clock. So that would take decisions based on the negative edge. So here it's a positive edge triggered clock. So whenever there is an edge, positive edge occurred, the data input, whatever it is sampled or it is then flip flop looks at the what is the data at this edge and transfer that data to the queue. Okay. So the every passage of the clock, the data is sampled and transferred to queue. So now if there is any change in between the clock period, if there is any data change, then that won't be reflected in queue, because this D flip flop look at D only at the passage. Okay, so now coming to the Verilog code, how are we going to develop this D flip flop code? So module, in module, so D flip flop DFF is the module name, where we have the input, in the port name we have input D. So this is input, we take 1 bit input, 1 bit data, and input, this is another one is a clock. So you can see that this is in sequential circuits, we have the clock or the enable. So here it's a clock. This clock needs to be generated through the test bench. The input clock should be given to the D flip flop during the testing. So input clock, it's 1 bit again, and output Q 1 bit, because D is going to be transferred to Q, and the output Qn, this is Q bar. Okay, so the complement of Q. So now we close the bracket and semicolon, so the declaration part's over. So now the declarations, input and outputs, we have declared for this D flip flop. So then if what would be this declaration, that is net type and reg declaration, this Q and Qn are declared as reg here. So the behavioral description will be going to the behavioral description of the D flip flop. So always at the rate passage of the clock. So this passage is the keyword here. So it represents this is a positive edge triggered flip flop. So passage of the clock. The clock is a variable which we can define as CLK or C, CLO, CK, anything, but passage is the keyword. So similarly, negage, I told you this negage is also a keyword when you represent the negative edge triggered flip flop. So always at the passage of the clock. Now begin, what is the code we are going to write? So it should, at clock edge, it should look at D here and pass it to Q. Okay, so I'm using the blocking statement. Still we have not introduced the non-blocking statement. So blocking statement D is copied to Q, and then Qn, there is a complement of D, so tilde D is Qn. Okay, so this is both are blocking statements, and we are ending this begin here. So within the always block, this is sequential. So what happens here, whenever there is a passage of the clock and then the D is assigned to Q, immediately this is blocking statement. So evaluation is immediate and it is assigned to Q. And then after this Q is assigned, the D which is there, whatever the value of D is made tilde and assigned to Q1. So this is an immediate assignment that we need to say the blocking assignment. We are doing the flip flop with the blocking assignment, but we'll also proceed with the non-blocking statements as well. So tilde D and Qn. So the Qn is getting the complement of this D here. Okay, so at the passage of the clock. So this is the flip flop characteristics actually made in the module, and you can see Q and Qn are getting the D values, which is, so we inside the always block, so we declare them as registers. So Q and Qn. So now let's see this, how the test bench work for this D flip flop. So till now we have not considered the reset in this D flip flop. So the D flip flop test module, D flip flop test is the module name of the test bench, and what are the inputs we have used in the module. So those modules here, D, that is declared as, and the clock reg also, and outputs are q and qn. So both needs to be declared as wires, and reg d and d clock, this will be automatically generated in the template, or need to, when we write the test bench, if this simulation tool doesn't allow, then you need to write this as a reg and d and clock, and outputs y in the test bench q and qn. So next, instantiate that d flip-flop module inside the test bench, which is going to be d flip-flop, the name, and the uut dot d, the port name of the flip-flop d, and d, this d is here is a local name, and dot clock, the clock again is here within the bracket, local signal. Dot q is the q referring to the module, and this q is referring to this, the wire which is declared here, and qn similarly, and this qn within the bracket is a local signal. So end the instantiation with the bracket and the semicolon. So now after instantiation, that in the test bench, you very well know that we want to display that what is the time slash t. The slash t represents the tab, d input, clock, q and qn. So we display this and then monitor the every variable d, clock, q and qn, so with along with the $time as well. So here initialize the inputs. So what are the inputs we are going to make? This d is 0, so clock is again, this is two inputs are 0, clock is 0, and end, this initial again end. So always now we need to generate the clock, because the input d required for the flip-flop module is given from the test bench. Similarly, the clock input is also needs to be given from the test bench. So they always, we use this always to generate the clock. We have seen the 2-3 ways of generating the clock using the always block and forever block, okay, in the previous lecture. So always hash 100 clock equal to not clock, so semicolon. So this always block doesn't have sensitivity list. So here is the hash after every 100 time units, here it's a nanosecond, so every 100 time units the clock is becoming not clock. So this is generating. So first clock is 0, and then made it 1 for 100 nanoseconds, and then 0 for 100 nanoseconds, and then 1 for 100 nanoseconds, and so on. So the after this clock generation, so the d input, the initialization part is done, and then the d and clock are made 0. After that the clock is generated. Then now how the test bench should have this stimulus. So what are the possible inputs it can get the module? So initial, begin, and then so we have this. Now clock is keep on moving from this according to the time of the simulator. So hash 100 d is the data input is 1 bit. We have seen 1 bit binary 0. The next 100 d equal to 1 bit binary 1. Okay, so we change the at 100, after 100, this implies that hash 100 after time 100 time units make d equal to 0. It's because already we made that initialization 0. After that, after 100 nanoseconds, d equal to 1. Okay, so in that case again after 300 time units make this d 0. Okay, so after 200 time units, d equal to 1. So this is this 100, after 100, after 300, after 200, and so on, end. So this stimulus, how this is how it is going to be transferred to the output of the flip-flop, this data. So let's see the waveform viewer. So waveform viewer, here is that you can see the clock which is here. This is 0 for 100 nanoseconds, and then 100 nanoseconds, and then 0, 1. Here you can see the clock is becoming 0 and 1. That, okay. So here is the passage of the clock. We can mark them, the passage of the clock. And then now see that d, which is 0 initially, and then it is next 100 nanoseconds made it 0, and first clock edge comes over here and it samples that what is the D here. Okay, so unless this and the D is transferred to Q, this point is Q. So you can see the immediate change in date Q. The red ones shows that it is unknown. Actually, it is not defined during this period. Qn initial 100 nanoseconds, when it is initialized, the flip flop is initialized, it doesn't give any output. Q and Qn are. So now at first clock edge, this getting the data 0, so it is going to 0. So the data is 0. So this data is 0 till this point. This is a neg edge. There is a data change, but you see that data, it doesn't, that D flip flop doesn't care what happened in between the clock edges to the data. So the next clock edge, this becomes 1. So 0 is maintained throughout this period. Okay, so this data, and then at next clock edge, it samples the data, it looks at the data again, and then check whether it is 1 or 0. So here it's 1. So it's a single bit 1. So it is changing to 1. This point. So it's not immediately this clock edge, it samples and transfer it. There is a delay involved in this process. So these delays, we'll look at it during the timing analysis. Okay, so now we just assume that this is going to be immediately transferred to Q. So but delays are involved in this propagation delay and the clock to Q delay, D to Q delay, and so on. So this is 1, and this 1 is retained, you can see in the Q, and the data is still 1. Okay, so the data is changing to 0 here. Okay, so at this clock edge it is 0, so it takes to this becomes 0 over here, the Q, the transferred here. And then similarly the data is maintained and data is changing over here, this is 1. But actually at the clock edge we should not be changing the data here as well as here. Either it should be, there should be a sampling window, or the window where which setup time and hold time violations can occur. So we'll be dealing all those timing details. So assuming that this data is changed here a little bit before or before, so that it takes this, it samples that 1 and gets to the Q. Okay, so this 1 is at this point, this is 1, so the 1 is maintained over here. Okay. So immediately the Qn, it is complementing fine up to this point, and again 0 here, and this is 1 and this is 0. So it doesn't involve this timing in parameters. So there is a setup time and hold time involved, meaning that at the clock edge will not be changing the data. So there is a window for which that data will not be changed before the clock edge. After the clock has become 1, the data should not be changed again for a smaller window. That is the hold time, and the previous one, what I said, is the setup time. So setup time, hold time violations, and then the delays, all those things we deal with them separately. And so now this according to the code, the D is transferred to Q by sampling at the clock edge. So the clock edge, what is the data, and the complement also have been obtained here, Qn, that is Q dash. So this can also be plotted in the log file separately. So you can see this is at 0 and 100 nanoseconds, D is 0, okay, and then clock is 1 and the Q is passed over here, okay, and then Q is 1. So that is retained at 200 nanoseconds, okay, but data is changing still. That is at 300 only it could sample because of the edge. So 300 only it could sample here, not at 200. Okay. So similarly at 400 you can see that 400, then there is no change over here. This is maintained. At 500, yes, it is checking that again. At this point, 0 is transferred to here, and 600, this is maintained. At 700, the change is again checked and maintained, and 900, this is also checked and then maintained over here next rest of the period. So this is just a print of the value, the variables what we have in the program. So this is a simple D flip flop without any reset or preset. In this case, is a positive edge trigger. So if you want to do that negative edge trigger, very well you can change the passage of the clock to neg edge of the clock, do the operation that is similar to this. So now coming to the D flip-flop with the asynchronous reset. So the flip-flop now what we had is having the D flip-flop, D and input clock passage, okay, Q and QN. So this is, we have a reset. So it's an asynchronous reset. So whenever irrespective of the clock here, that is whenever there is a reset is pressed, the Q should go to 0. Okay, that is reset is made 1. If reset is made 1, then Q equal to 0. Otherwise, every passage of the clock, and then if reset becomes 1, reset becomes 0, this needs to be checked with the clock here. So the clock anyway this performs like a D flip-flop, that clock edge, every clock edge it samples the D and pass it to Q, and if reset is 0. Okay, so D flip-flop with the reset, input at D and input is again the clock, reset also an input. Now we have to add that 1-bit reset, and output is Q and Qn. Okay, so close the bracket with the semicolon. So this is the declaration part done. Now what are the reg? Q and Qn are the reg which is going to be used in the always block. This is a behavioral description again. Let us see the always at passage of the clock or passage of reset. Okay, so here in the asynchronous case, this is asynchronous reset. In the previous case we didn't consider the reset, only passage of the clock, that data is transferred, and here the passage of the clock, it samples the data, it looks for the sensitivity list contain the passage of reset as well. If reset is 1, then you make this Q 0. Okay, so that's reset is 1, you press it and it going to 0. If reset else, 0, if Q is 0, then you need to define this, what is Qn also, because we have taken that Q1 also as output. Qn is 1-bit 1. These are all blocking statement. Okay, so and end. So if reset is 1, then make this 0 and 1. Else if reset is not 1, that is 0. Okay, so then go to the begin. D is copied to Q, and D tilde is copied to Qn. Okay, so then end. So we have the priority is given to reset. You can see that this is the priority. If reset is 1, if this is 0, else go to this else go to the Q equal to D or Qn equal to tilde D. Okay, so in the asynchronous reset we have this sensitivity list, both, not only the clock edge and reset as well. So now the test bench, look at the test bench, module flip-flop reset and the test. This is module name. Inputs are D, clock and reset. You can see the addition here, and the output Q and Qn. Okay, so initialize this. Next one is you can initialize the, after declaration, initialize the flip-flop DVFFR UUT, D clock. You can observe the change, the reset Q and Qn. Initial begin, that display is giving the variables D, clock, and then reset Q and Qn also. $monitor with respect to time, the D, clock, reset Q and Qn. Also the initialize this inputs D, clock and reset. So reset also is made 0 initially. Okay, and then always #100 clock equal to clock not. In the, this is a clock generation as we had seen in the previous example also. So the now the addition is only the reset. So add the stimulus here, initial begin. So first 50 nanoseconds this reset is made 0, after that the reset has become 1, that is #50. After #50, so 50 it becomes 1. So next 50 reset is again made 0, the data is given some value. Here data is assumed to be the value which was initially D equal to 0, and after that some 70 reset is made 0, D is 0, and then reset is maintained 0 and D is changed, and then reset is also, this is 0, so data will be passed to Q. is similar, then we see the data reset change, that is to check this whether when a reset is 1 in between, that data is 1. So what happens here? Okay, so this will be made to 0, right? So again, if you maintain the reset, whatever the change in data, whatever may be this data is made 1, so end. So all these conditions, this 1 1, this would be 0 only, and reset 1, the data whatever is here mark passed to the queue. So let's see, these are the various conditions of the inputs, that is you can have the stimulus exhaustive, so that the flip-flop can be tested for the different inputs. Getting to the word output here, clock, you can see this is 0 1, again 1 0 1. You can see the clock edge, which is the passage of the clock. Now the D, so if you look at the reset, it is initially 0 and then made 1, okay, this is made 1 and for some time, and then it is 0 here. So at this is 100, okay, 100, and this was made 1 at around 50, yeah, 15 nanoseconds. So and again this is made 0, so that D is passed to Q. So during this period, the clock, when the clock is 0, you can see it is here, the reset is made 1, so the input of that. So when reset is 1, you can see the data irrespective of the clock edge, okay, so the data is made 0, okay, when the reset is 1, this made 0, and here it is 1, the Qn will be complement of it. So this is where the reset is 1, and then reset made 0 just to pass this D to Q. So here D is 1 at the clock edge, so it samples it and then pass to Q, and this becomes 0, and Qn is 0. And this, though the data is changing in between, you can see when the clock is 1 that there is no change in the Q, okay. So this is maintaining this 1 throughout till next clock edge, okay. So though the data has changed here at this point, and that won't be reflected in Q, so the next clock edge, the data will be sampled, and then, but if reset is 0, then only it will be passed, otherwise it becomes the data will become 0. So reset is 0, kept 0 in this period, during this period. So the next clock edge, this data 0 is passed to Q, transferred, and then here Qn is becoming 1 because of that, and the data change occurred in between, so that is not reflected in Q, okay. So because this is 0 maintained, and next clock edge, yes, this data is 1, it is again changed to 1 here, okay. So this point becomes, it is 1, I can write it in the right hand side. So this is 1, okay. So Qn becomes complement of it, this is 1, so becomes 0 here. So data is changing after that, so that is not could be recognized by this D flip-flop, and it maintains this D up to the next clock edge would be here. But you can see that in this point, it samples here, it is 1, it should maintain up to clock edge here, but in between the reset is made 1, that reset is made 1, okay. So in between this reset is made 1, irrespective of this clock edge, what is the data, this data, whatever may be the data, this immediately brings it to 0, the Q is made to 0. So reset is pressed over here, and then this reset is on all the time. So whatever the change in data or clock edge is not recognized on this here. So that's the clock edge, you can see at the clock edge it is sampling it, but you can see that the reset dominates, or so reset, it becomes 0 over here. So because of the reset, the data is 0 throughout. So this is asynchronous reset of the D flip-flop over here. So now the case of log file, which is printing this whole behavior at 500, you can see at 500 here, sorry 50, so 50 here. This is D is 0 here, this point, okay, and then clock is 0. You have this reset is 1, okay, this point, and then Q and Qn, okay. So similarly you can observe this 100, and then when the data is passed at 100, yes, it looks at and it gives to the D value to Q, you can see, and this Q is maintained, okay, though the data is changing in this places. So if we take it at suppose 500, so let's look at this point at 500, okay. So the 500 the Q is 1, okay, 500 the Q is becoming 1 and this is 0, okay. So at we take this point where reset is becoming 1. So here D is 1, but Q is 0 on all these things, okay. So D because of the reset it became 0, though the data change occurred here, okay. So this is the behavior of the D flip-flop with asynchronous reset and D flip-flop with synchronous reset, say. So what's the difference between this synchronous reset and the asynchronous reset? So here the module, we have the module name the synchronous reset. For a change we give this D as 4-bit input data, and the reset 1 bit, and the clock we have the output reg getting the 4-bit 0 to 3 Q, and Qn also will be 4-bit, which is a complementary one, close the bracket with a semicolon. So now this is the declaration part, full declaration, and you can observe the reg declarations also. We will be using this within the always block. So now the code always at the rate passage of the clock. So it is synchronous reset. So this is with respect to the clock only, the reset, okay. So if the passage of the clock reset is 1, then make it data 0, or the data, if reset is 0, then pass the data to Q. So if reset is 1, okay, this is happening, this can be checked only the sensitivity list. You can see that if there is any change, this whole thing can occur, the code what is following, only looking at the passage of the clock, okay. So passage of the clock, reset is 1, make this Q 4-bit 0 0 0 0 0, and then else the begin D is passing to Q, and then D tilde to Qn. Okay, so the Q should be given 0 0 if reset is 1, else if reset is 0, then pass this D value to Q tilde D to Qn and end. So there is no other change here. You can see the sensitivity list change in the between the asynchronous reset and then the synchronous reset. So in synchronous, the test bench, the reset can be pressed anytime with irrespective of the clock, whereas here it is with respect to the clock. So D flip-flop, synchronous reset and test. So the inputs are 4-bit D input and reset and the clock. So output 4-bit and then wire and Qn instantiated DFF reset U dot D dot reset dot clock dot Q and dot Qn. This is the same as the asynchronous one, only the data bits are different in this case is what are the data bit you will be doing. So the integer here, because of the data bits, and we would like to have the more, so declare this I as integer, initial begin. So initialize these inputs D equal to 4-bit 0 0, reset is 1, and clock equal to 0, and then end. So now going to the stimulus. What is the stimulus? So generate this clock. It's a clock generation as 100 clock equal to not clock, 5 megahertz, 200 nanoseconds, 5 megahertz clock, initial begin. Display them because we want to monitor it in the console or in the log file, also in the this is monitor and display. This is display, that it gives the variables over there, and the monitor the time and the other variables D, reset, clock, Q and Qn. After hash 50 we made reset 0, and then hash 150 reset 1, and hash 100 reset 0. Okay, so this is reset 0. Clock is actually keep on generated here, and you'll see end, initial, begin. So what is the input for I equal to 0 using the for loop I less than 16, I equal to I plus 1. So the begin, for I assign this I to D, that is the input, the data generation actually. So hash 70, where after 70 again increment this I to 1, hash 70 and increment this 1, and then assign it to D. So end, here this begin ends over here, and this begin end here. So only one for loop is used to do, because D is going to be a 4-bit data just to generate them, and the reset changes have been done over here. So we see the output, which is waveform viewer output here. The clock, let's take the clock first. The clock edge, here is the clock edge, here is the clock edge. Okay. And the data, it is starting at initially there is no so the reset is 1, you can see here reset is 1. Okay, reset is 1, and the clock here, you can see that even though reset is 1 and then the data is not 0, you can see x x x x x x. So it checks at the clock edge, and reset is 0, then the data would be passed to here. Okay, if reset is 1 at the clock edge, then it is again passing this, then Q will be 0 0. Okay, so 0 0 1 at this clock edge, and the reset, this is synchronous reset. So synchronous, the reset is 0, so the data is passed to here. So 4-bit data at 0 0 1 can be seen over here. And in between, because we have given this I 70 time units, so it is changing 0 0 is continuously, this data is changing in between. So at this point here this is negative edge, and there is no concern, it is not looking at the data, but the reset is made 1, you can see reset is made 1. So this reset would be giving the, because of the clock edge information is already there, so it is looking at it. And but you can see that reset 1 also doesn't reflect here. Okay, so it doesn't reflect, the data is still 0 0 1. Okay, so, and the reset is made 0 at this point, so the next data is passed to the 0 1 0 0. Okay, and the reset is made clock 1, and then reset is 0 all these times. Okay, so reset is 0 all this time, so there is no problem of that data being blocked or made to 0. So this clock edge, what is the input, it is given over here, and at this clock edge the 4-bit data is passing over here, and you can see the data is being maintained. And at this clock edge, this is exact data change, but this should not be occurring in the real time, that is when we consider the timing and timing also. So there should be a setup and hold violation if we do that. So in making to 1 0 1 0, at this point the data is 1 1 0, so that is also getting into the Q. Okay. So the Qn complement of this, every bit, this is every bit complemented, every bit complemented, every bit tilde, every bit complemented, and that is the output of Qn. Okay, so this reset is 0, so though the reset is becoming 1 here, you can see it doesn't transfer this code data to Q. Okay. This is the increment of I, which is shown over here, 0 to 1 and 12 13 and so on. So the Vivado, the print outputs are shown over here, that 50 nanoseconds and then 70 nanoseconds. Okay, the data, because of this change, it doesn't, Qn doesn't have it, the data is passed over here. Okay, this is, and then here it is maintained. Okay, so whenever this clock 1, it is clock 1 changes can be clock 1 also can be checked, but the data change is reflected or not, because this is not reflecting. at this point the edge of the passage of the clock is checked. So you can see the outputs plotted over this here. Okay. Q, and this is the clock, and then here is the reset. This is the reset column, this is clock Q and Qn, and this is the data D. So the remaining part of this, the data change, and this is the reset is 0. So clock, passage of the clock, whatever the data was maintained. So here you can see the data being passed to this one and maintained here, and this passed over here and maintained. So in between that clock period, it is not the changes are not reflected in the queue. So this is just exact representation of the waveform editor, and it's just a printing of this output over here. So next, coming to the D latch. So we have seen this D flip-flop with the without any reset or preset, and asynchronous reset, D flip-flop with asynchronous reset, and D flip-flop with synchronous reset. So if you consider this latch, it would also store the 1-bit information or the data bit storage. If D is more, then it can be used to store the information. So the latch here would be always, it's not, these latches are not edge triggered devices, that is clock edge triggered. It is a level triggered devices. Okay, so when the enable, here you can see the clock which is replaced with an enable, it is not having the clock symbol here. So it is an enable, this is level triggered, and whenever there is an enable is 1, whatever the data change or the data would be transferred to Q. Okay, and it's complemented. So there is no reset involved. Let's see how to form this latch in the Verilog code. So module and the end module, we have the latch module. D is input, enable is 1-bit input, and then Q is the output, and Qn we didn't take it, it can be, it is not used, not complemented, the complemented output is not taken over here. The reg is Q, and then always at the rate enable or D. Okay, you can see whenever there is a change in enable or D. So the sensitivity list contain all the inputs here. Okay, so as in the case of asynchronous reset, whereas in the synchronous reset we didn't have that reset to be checked, or if there is any change in reset, should not be independently doing it. So it should so the enable or D, any change in that begin. If enable is 1, okay, this pass D to Q. Okay, end. So if you see the code, there is no else statement. This will infer automatically a latch. This is a intentional latch. Okay, so there are accidental latches in the code. If you miss the other condition else, yes, it would form a default case in the case of case statements, that would form a latch. That is the inference of the, here we are the behavior of latch we are doing. So if enable is 1, then pass D to Q. We are not telling what to do to if enable is 0. Okay, so that infers the latch, that is taking the last Q values in the, if it is else, that would be same, that would be remain same. Here is the latch behavior we would see in the using the test bench. So module, there's a latch test, that's a module name. Input reg is D, and enable also. Here the output is Q, only Q, not Qn. We have not used in the Qn. Instantiate this latch module here, latch ut.d enable and Q. Okay, this is, and the initial begin display, where time is time, D, and enable and Q, these variables have been to display in the log file, and the dollar monitor using the, all these things needs to be monitored, printed over there in the console. The initialize the inputs, D enable, there is no clock over here, so wait for this 100 hash 100, and then end module you have add the stimulus here. Okay, hash 100 enable 1-bit 1, D equal to 1-bit 1. Okay, so after global reset, after then after 100 nanoseconds, after that enable is made 1 and data is made 1. Okay, so then enable is made 0, data is made 0. After that, enable is made 1, data is 0 still, and the data is enable is 0 and data is 1, enable is 1, data is 1, and so on. So there are various combinations of this input, the change in the enable. So if there is an enable 1 and data input is just passed to this queue. So let's see the output here. The enable, there is no clock generation as I told you. So this is the enable signal. So enable signal is 0 over 100 nanosecond, and then 100 nanoseconds we had this global reset as well. So the enable is made 1 here. Okay. So you can see that we have not used the passage of the clock or negage of the clock, passage of the D or passage of the reset or negage of this. This is level triggered. So whenever this enable is 1, what is the D? Okay, so it is not looking at the edge. At the edge, it is looking at the duration of enable 1. So in this duration, when it is level 1, what is the data here? Okay, so after becoming 1, what is the data here? So the data is 1, so it is passed to Q. Okay, so the same thing, but the data is changing over here in this point, but still, okay, so you can see this enable till this enable 1, this is 1. Okay, and when the enable is 0, I mean it is we didn't say anything to the code what should be done, so it retains the value, that is 1 value, while the last Q value is retained. And when enable is becoming 1 again, so the data is 1 again, this is 0, so it becomes 0. Okay, so the Q is becoming 0. If we change it over here to 1, for example, this input, if we change it over here 1, that would have been reflected here as well as 1. Okay, whatever the change in the enable. So right now this is not changing, so it's maintaining 0, and the data is changing over here, and that is not that's not reflected over here, because this is not changing during level 1 of the enable. Okay, so the last state is maintained till this point. When the enable is becoming 1, the 1 is passed over here. Okay, this is 1. Okay, so this change is avoided, and this change is also avoided in the latch output. So latch is maintaining the previous output when enable is 0. Enable is 0, it just maintains that. So because that means you are latching this the previous last Q values there. Okay. So the log file which would give that at 200 the 0 will this is giving unknown, and at 200 nanoseconds when the enable is 1, D is going to Q, and enable is 0, so that is maintained the last Q value, and when enable is made 1, the data is changed and it is maintained over here, though the data is changing, and enable is 1, this is passed to 1, and this is maintained over here. So we will be looking at this blocking and non-blocking assignments also in the next lecture. So we had seen the D flip-flop behavior, the behavioral description with blocking statement. Okay, the simple that D flip-flop and the without any reset, and 2 types of resets also we had seen with how to write that with always block, and the if else statements with the case the latch. If you don't consider the else condition, then how it is forming a latch, it's an intentional latch. This kind of thing, accidental latches also can form in our code, so it should be that the accidental latches should be avoided in the code. But if it is intentionally we want to make the latch, yes, this condition, the else condition, needs to be removed, and if you use the if else or in the case statement default conditions can be removed. So we'll see the incidental and accidental latches in the synthesis process. So the D flip-flop will continue with the flip-flops and the how this conversion of flip-flops, how these flip-flops are used in the counter design and the counter other sequential circuits as well. Thank you.